Hello, everyone, and welcome to Physics 4A, General Physics, Summer 2020. I hope you all are doing well. I hope you're all healthy. My name is James Boyd. I am your instructor. A little bit about me. I graduated from the University of California, Irvine, doing primarily biophysics research. And I've been teaching at IBC for the last couple years. I went to community college when I began my college career and transferred to the University of New Mexico. And my hope is that by the end of this course, I will help you develop the skills and competency to do well in your physics and science classes. That being said, this video itself is a little bit of an introduction and then a really, really long video on math. Probably a lot longer and a lot more boring than any of our other videos will be, but it is necessary because some of you have either forgotten or never had trig or some of the calculus or haven't had it yet or just aren't familiar enough with it. Everything we do in this video, we are going to cover again as we need it, but it's here for your reference. And so to start off, one thing I'd like to show you, if we go into Canvas here, in Canvas, you have the ability to, this is our Canvas webpage. Under textbook, you can click on Wiley Plus, and assuming you have a Wiley Plus account, you have the entire ebook. Now, about our book, the physical copy of the book is actually pretty terrible. It's not very helpful. It's not very useful. You don't need it. Our entire book is online. In addition to being online, we have a whole bunch of simulations and office hour videos. These are like Khan Academy sample problems, video sample problems. But as you can see, here we have all of our chapters. In fact, the entire book is here. I hope that's not just for me. I hope that's for you as well. You have MCAT and math skills interactive exercises. You can go to any section. So for today, what I want you to do is I want you to go through the practice Wiley Plus homework assignment on this. It's not worth any points, but just familiarize yourself with Wiley Plus, how it does things, how you have to enter scientific numbers sometimes, just so that you can play around and you're not worried about points. My general philosophy on homework is you have a week to do it, and I give you 10 attempts. I don't want you to lose any points on homework. If you're having issues, I'm going to publish a little introductory letter for you guys. But if you're having issues, get help from your friends, get help from me, get help from a tutor, do whatever you need to do. But I really want you to try to do the homework on your own, work at them. One of the big things that you've got to do in this course is you have to do problems. Problems, problems, problems. And I talk about that in the introductory lecture. I'm not going to go too much over it here, but you've got to develop your intuition and your skills, and every physics problem is different, so you can't memorize them. One huge word of warning: every problem in Wiley is online somewhere. Someone solved it on Chegg or wherever. You can find the answers. But if you do that, the problem is your brain doesn't remember it. You have to do the work. It's like running a marathon or learning a language or learning piano. You have to practice to get your muscles working. And the only way you can do that is by doing problems without any help, without any safety net. Secondly, once you've done those problems, get with other people in the class, talk about the homework, tell other people how to do the homework. You'll find out whether or not you really know it. That's a huge key. But basically, your entire book is online here. You can go through and look. If you wanted to go to chapter 1, chapter 1's right here. Chapter 1's really dumb and really small. But, and then there's all these additional sample problems. There's a whole bunch of stuff you can do here, which is great. And I urge you to do it. I'm not going to assign it, but I really urge you to do it. I know we're going to be on a time crunch. We're going to be learning really fast. And I'm going to try to make it useful to you and help you get through it. But there's a lot here that you can dig into if you really want. So please, please, please do that. One other thing, your homework will be found in these assignments. Your quizzes will be in quizzes. I'll post the syllabus. Hopefully it's posted already. And then these videos will be in their own little module. Okay? That being said, let's move on to the highlight of today's lecture. And that is our math skills chapter. It's either called chapter 0 or chapter 45, depending on where Wiley puts it. I don't know why they do that, but in this particular class, I focus a lot on the problem solving, meaning I want to know how you set things up. I want to see pictures of the system, of the objects. I want vectors drawn. And from that, I want you to be able to write equations. And while I'm not saying math takes a backseat, it's definitely the easier part of answering the question. You're going to find we're going to do 90% of what we do is algebra, to be honest. We need the calculus for the derivations of the equations of motion, but we don't need it so much as in the form of, we're not going to be doing a bunch of integrals. We're rarely going to be explicitly doing derivatives. We're going to be using the derivatives, but we're not going to be sitting down and trying to find the derivative of 3x ln of x plus cosine of x, right? What we're going to be using is equations derived using derivatives and integrals, and you'll see that pretty fast. This lecture is a lot of math. You are going to be bored to death by the end of it. I provided some sample problems. I will give you a huge hint. Tomorrow's quiz is on law of cosines, so please make sure you look at that section. But other than that, I really want it just for people who need it. So you may find you don't need any of this. That you're all good, great. You might not have taken trigonometry, or you took it and you don't remember it. Trigonometry is a lot of what we do. We have to be able to figure out what angles vectors are at. And so we need to know how to do trigonometry and geometry. And then there's a little bit on derivatives, a little bit on integrals. There is a pretty major concept of dot product and cross product, which are how you multiply what are called vectors. But we are actually going to study vectors tomorrow. So tomorrow is all about vectors. The reason why is vectors are our main tool for describing a physical system. So a little bit of history and kind of a focus on what we're trying to accomplish in the course. Isaac Newton basically figured out that you could describe the world by the motion of objects. And he called this kinematics and dynamics. He basically said that if you describe something as a force, and a force is something that changes the acceleration of an object, then you would know how it was going to move. And from that, he developed the laws of physics, the big laws of physics. And so what we're doing in this entire course is we're trying to understand how an object's moving and understand and predict how it will move in the future, or how it may have moved in the past before we started investigating it. And that's all we're doing. We're simply investigating motion. And we're trying to figure out some of the causes, or at least the effects, of things called forces, which we'll get into Thursday. Thursday is when the course properly starts, with a lot of talk about Newton and a lot of fun stuff. a lot of thought-provoking stuff you probably never thought of. So the fun starts, I'm sorry, Wednesday. But before we can get to Wednesday, we need to make sure that we understand the language of physics, and the language of physics is math, specifically vectors and how to use them to describe motion. We're going to talk about this a little bit later, but the difference between a vector and a number is a vector has direction. It has a very clear specified direction. So when we get there, we'll get there. I'm going to start off with something super simple, and that's the prefixes on scientific numbers. This might seem a little dumbed down. You probably know it. That's okay. But you're going to be going through Wiley Plus, and you might not realize it when it says megajoules with a big M and a J. What it's talking about is mega is 10 to the 6th. One thing I should say here is you can actually, the beauty of scientific numbers, if you don't know, people always mess this up, but let's say I want to multiply, let's say I want to multiply 10 to the 41st times 10 to the minus 19. Another way of writing that is 10 to the 41 over 10 to the 19. Minus means it's in the bottom. You simply add them. If I add these together, I get 10 to the 22. So I could have 2 times 10 to the 41 times 3 times 10 to the minus 19. I would get 6 times 10 to the 22nd. That's why we use these, that in really big numbers. You're all familiar with centimeters. There's 100 centimeters in a meter. Incidentally, a meter is basically a yardstick, around 3 feet. And in decimals, it's 0.01 of a meter. Millimeters are 1,000th of a meter. There's 1,000 millimeters, so they're 10 to the minus 3. Micro is 10 to the minus 6. This is pretty much getting down to the level of cells. Nanometers are light. Light is in nanometers. Pico is something astronomers use. It's 10 to the minus 10. There's unit reasons why that makes it more convenient. You all know kilograms are 1,000 grams. We don't use grams in scientific notation or SI units. We use kilograms. Mega is 1,000,000. Giga is 100 million or 1,000 million. Just so you know, they pop up sometimes in Wiley, they pop up in problems. They're shorthand for saying 10 to the whatever, okay? They're just there in case you need to reference it. It's not a huge deal, but yeah, I just felt like going over it. As I said a moment ago, in this class, we are going to use SI units, Scientific International or whatever they are. In those units, mass, and we're going to talk about mass in a couple days. It's not weight, not the same thing, but mass is measured in kilograms or thousands of grams. If you've done any labs in high school or other college, kilograms are pretty big, pretty heavy. 100 grams is a decent sized weight, you know, a heavy ball or something. A single kilogram's a pretty heavy weight. So it's a little weird that we use kilograms, but that's what we use. Time is in seconds. We are going to use distances in meters, always meters. Angles, okay, so we're going to talk a lot about angles today. But your calculator has a setting of rads or degrees. And what I should note is that degrees are entirely made up. We decided that there were 360 degrees in a complete circle, perfect circle. That same distance is divided up into 2 pi rads. So 180 degrees is pi rads. The difference between the two is a rad is a pure number. A degree is not. A degree is simply made up. So 180 degrees is the same thing as pi rads, but if you use pi rad and you do something like the trig functions, the inverse trig functions will give you your answer in radians. And it's important that you understand that this is a real number, this is something made up. And then in fact, neither of these are actual units, they're convenient notations. We'll talk a lot more about that as we go, but the three main units are mass, time, and distance. And those are in kilograms, seconds, and meters in SI. There are a ton of other units. Every scientist, it seems like in history, came up with their own units sometimes. But these are the agreed upon standards that we're going to use. The units of force are called newtons, and a newton is a kilogram times a meter times a second squared. So when we get a problem, let's say we had a problem where we were told that a 110 gram weight was falling 57 centimeters in 3 years, okay? We would need to convert all those things into kilograms and meters and seconds. And we'll talk about how to do that in a minute. But otherwise, your units wouldn't be newtons. So why do we care? We care because of consistency. You're going to find when you're doing labs that you're going to have times in the labs where you forget that you're in centimeters and you're trying to compare something like the acceleration due to gravity, and you get some god-awful number like 1,000. And you're like, oh man, my number's off. And it's, well, you didn't convert to the proper units and you were actually in centimeters, and therefore, instead of getting 9.81 meters per second squared, which is the acceleration of gravity at the surface of the Earth, you got 981 because you were in centimeters. And you were close to that. So the reason why we actually care is it's a way to check our math, right? If I have a 10 kilogram mass, right, that's moving at 5 meters per second for 5 seconds, okay? And I want to know what the force acting on that is. I can multiply this through and I see that I get 10 times 5 divided by 5 is 10 kilograms meters per second squared, okay? I know these units are newtons. So I know I've got my math correct. That's a pretty bad example, but in a sense, they're useful for checking yourself. Always check your units. A little bit of a hint, too, in classes that aren't as math heavy, science classes, like chemistry, a lot of times you can figure out what you're being asked for simply by your units. There's something called joules, and joules are energy. They're used in everything. And joules are Newton times meters. Okay, they're force times distance. And if you know that, you can figure out what you need to do mathematically to get the energy in the system. It's a really nice shorthand method of checking the logic and consistency of your math. And that's why we care. That's why we need units. That's why a lot of professors will drum into you over and over and over again, list your units. I care about units at the end, okay? I do want to see a proper answer in units. Along the way, I don't care. They're for you, and it's important that you know what the units are, and it's important that you know what you're supposed to get, but I'm not going to count you off a bunch of points because you didn't write Newton meters. I might count you off a point sometimes on an exam, a small point, and a point's almost nothing. If I feel like you were confused about the units. If I think you knew what the units were and didn't include them, it's probably not that big of a deal. But if you clearly don't understand the difference between joules and, say, angular momentum, then yeah, I'm going to count you off. So don't worry too much about it. We'll talk about it. I'll try to be consistent with it. I won't always be consistent, unfortunately. So if I miss some units here or there, don't be too upset at me. Anyway, so the next thing that we want to talk about is converting units. Sorry, my dog needed to go outside. So unit analysis or converting units, really probably familiar to you if you're in like chemistry or one of those sciences. You've probably done it a bunch. But for those of you who have forgotten or don't know how to do it, let's talk about it. One of the most useful approximations is actually seconds in a year. I'm going to teach you a trick about seconds in a year that you can always remember. But let's talk about how many seconds there are in a year. So we know that there are 365 days in a year, in 1 year. And we want seconds in a year. So the first thing we do is we want to convert days to hours. Okay, so in 1 day, how many hours are there? There are 24 hours. And in 1 hour, how many minutes are there? There are 60 minutes. And in 1 minute, there are 60 seconds, okay? So what unit analysis allows you to do is cancel top and bottom. Cancel top and bottom, cancel top and bottom, and what we see is then we just multiply through these numbers. If I multiply 365 times 24 times 60 times 60, I get 3.1536 times 10 to the 7th. So I get 3.15 times 10 to the 7th seconds in a year. 3.15 is really close to pi. If you want a shortcut, you can go from, you can use simply pi. There are pi times 10 to the 7 seconds in a year on Earth. It's an extremely useful shortcut so that you don't have to do this. Let's do another one really fast. Density of water. So the density of water is 1,000 kilograms per meter cubed. Another way to remember it is that it's 1 gram per milliliter. So we're going to talk about that. Let's show that this is actually 1 gram per milliliter. So 1,000 kilograms over a meter cubed. There is, in 1 milliliter, there is 1 meter cubed. If you're not, don't worry too much of this unit. This is a chemistry unit. And then how many grams are in a kilogram? Well, in 1 kilogram, there are, I'm sorry, centimeter cubed. Let me go back. I realized I was about to do something dumb. In 1 kilogram, there are 1,000 grams. And remember, we want grams per milliliter. And then, okay, in 1 meter, there are 100 centimeters. But we need to cube this. We need to multiply it 3 times. And so 100 times 100 times 100 is 10 squared times 10 squared times 10 squared, which is 10 to the 6th. Okay, we'll come back to that, or I'll put it right here. 1 meter cubed over 10 to the 6th centimeters cubed. Okay, that's what this equals. And then in 1 milliliter, there is 1 centimeter cubed. Okay, and so we see that this 1,000 times 1,000 gives us 10 to the 6 over 10 to the 6. They cancel. And we get 1 gram per milliliter because our cubic centimeters, our cubic meters, our kilograms all cancel. Okay? So if you're in chemistry class, you may use, for the density of water, 1 gram per milliliter. For us, we will in general use 1,000 kilograms per meter cubed as the density of water. Because remember again, our units have to be kilograms and meters, okay? And the density of water is 1,000 kilograms per meter cubed. We'll talk about that when we do density. It's not that important right now. It'll be important later. The final unit analysis type deal that I want to show you that's also useful is because you know there are 2 pi rad in 360 degrees, okay? You then also know that there are pi rad in 180 degrees. Now, if you want to convert to radians or degrees, so let's say that we have pi force radians, right? And we want to know how many degrees that is. Well, if we divide this by pi rad over 180 degrees, the pi's cancel and we get 180 over 4, the rads cancel, degrees. That is 45. Okay, you probably already knew that, but if I want to know 30 degrees in rads, okay, I have to flip it. So I have 180 degrees are in pi rads, and therefore I get pi over 6 rad. Okay, 30 degrees is pi 6 rad. It's useful if you don't have your calculator with you for some reason. We're going to talk a little bit later about how to remember what the various angles are. There's a little bit of a trick, a little bit of a shortcut, so that if you're ever taking a test, you're taking the MCAT, you're taking some engineering test, whatever, and you don't have a calculator, you can ballpark the number pretty easily. It's worth knowing. The less, I'm going to say an aside right here. Whether you're doing your homework or taking an exam, the less time you can spend messing around with your calculator, the better you are. And you guys all probably know this. How much time you waste putting numbers into a calculator over and over that are wrong or messing things up, if you can get away from that, get away from that. Get used to just writing stuff down. I will also tell you that on an exam, if you don't have time to finish off a sum, giving me the equation with the proper numbers in it without giving me the final answer, but the equation's right, you just didn't put it in your calculator, I'm absolutely fine with that. As long as the numbers are right, I'm absolutely fine with that, okay? So you could give me this part of this answer without converting it down to 3.15 times 10 to the 7. I'll take that answer. I understand that you guys are in a rush, and that part of it, anyone can do. The part I'm testing you on is that part in the box. Do you understand how to get there? Okay, so just bear that in mind. Don't waste time with your calculator. Don't fight your calculator. Don't fight yourself. Spend time efficiently, okay? I'm assuming everyone understands significant figures. Adding and subtracting them, what it boils down to is you keep the least amount, okay? As you can see here, if we add 4.21, which has 3, to 13.457, which has 5, we get 17.667. We only keep 3. We keep the same as the least, and we round. Okay, so we round it up. Multiplying and dividing, same deal. If I'm multiplying these 3 numbers, An important note here is this is 3 times 10 to the minus third. So this is only one significant figure. So I'm only going to keep one figure here. I'm going to keep 8 times 10 to the minus 2. Okay? We don't really need that too much in our class. You'll sometimes run across Wiley being weird about it. So make sure that you round right, you do your significant figures right. I will tell you on an exam, I don't want 15 digits from your calculator. I want something useful, so don't give me 15 digits. Give me 2 or 3. Give me whatever the significant figures are. If you're off a little bit, I'm not that upset about it, but I'll be more upset if I'm getting 15 digits in an answer. I don't need that. I don't want that. I want something logical and reasonable in an answer. So that's pretty much all the easy stuff. We're going to move on to geometry. A little bit about geometry. And then we're going to get into some trig. So the first thing in geometry that we need to talk about is arc length. If you haven't taken trig or geometry in a long time, you might have forgotten about arc length. We're going to use it a lot. But let's say we have a radius of a circle, and we're going to travel some distance around that circle. Okay? And we're going to keep r the same. This distance, and so this is some change of angle, these r's are constant. This distance s is arc length. And the formula is pretty simple for arc length. S is equal to r times theta, or more precisely, delta theta. To prove this to yourself, if we went all the way around a circle, we would go all the way around the circumference. And the circumference is 2 pi r. So our S would equal 2 pi r. And that would equal r times really our change of angle. And we can see here that if we cancel r, our change of angle is 2 pi radians. So we also see here that what we've got is we've got a pure number. It's not 360 degrees. In fact, if our angle was 360, 2 pi does not equal 360. It equals 2 pi, right? 2 pi radians, okay? So that's arc length. We're going to use it a lot later. When we do rotational motion, we're going to use it a lot. And other than that, there's not a whole lot to say about it. I believe it's in the math skill chapter, so I brought it up here as I went through and looked at things I wanted to talk about. It was on there. Area formulas. I know you all know area formulas, but for those of you who don't remember, the area of a triangle, a right triangle specifically, is 1/2 base times height, where this is the base, this is the height. It's half of that, if it's a right angle. Because you basically have a rectangle and you have half the area of a rectangle. A disk, the area would be pi r squared. Whatever the radius of the disk is, pi r squared. The surface area of a disk, so surface, or of a sphere, I should say, is 4 pi r squared. And for a cylinder, if we include both the top and the bottom of a cylinder, it's, remember, as we go up, we could integrate this and get this as an integral and solve it. I don't want to do that. We know that this is the height times the circumference. So however tall this thing is, as we go around, plus 2 times the area of the top and bottom, which is pi r squared. So if for some reason we need the area of a cylinder, that's what it is, the surface area, not the volume. We'll talk about the volume in a minute, okay? There's an idea about cross-sectional areas and things like that that we will talk about down the road. But just go back through and review your area formulas. If you've got them on a folder somewhere, you got them on a cheat sheet somewhere, keep them with you. You never know when you may need them. Same with volume. Volume of a sphere, if you don't remember, is 4/3 pi r cubed, where r is the radius. Volume of a cylinder is simply h times pi r squared. It's as if each of those little discs, and you integrate up and you get h of those little discs, whatever h happens to be. That's really all the volumes we need. You know, a cube is length times width times height. The key point here is area is meters squared, volume is meters cubed. Arc length is obviously meters. If you don't remember your area formulas, or you've never learned them, or you don't have them somewhere, write them down somewhere and just keep them with you. Like I said, you'll need them at some point for a problem, and you need to remember them. They may not be given in Wiley Plus, so you just either need to integrate them or figure them out. But almost everything we do will be a useful, easy shape, a shape with what we call symmetry. We'll talk about that later too. Symmetric shapes, meaning spheres, cylinders, rectangles, squares, triangles, things with symmetry. All right, so now I think this is actually where many students have serious problems. They have a serious deficiency in their math, is their trigonometry. Trigonometry is the study of angles and the functions associated with angles of different types of triangles. It says on here right triangles, but really trigonometry is all about the trigonomic functions: sine, cosine, tangent, secant, cosecant, cotangent. We're only really going to need sine, cosine, and tangent. Occasionally you run across things where you need the other ones. If you know them, great, use them. If you don't know them, don't try and learn them during this course. But you need to know sine, cosine, and tangent. So let's talk about what that is. So right triangle geometry. So a right triangle is a triangle that has a 90-degree, it has a 90-degree angle, and we denote that with a square here. Okay, that means that this angle is 90 degrees. And it could be, the angle could be anywhere. But in general, we're going to assume that this is along the x-axis and that this is along a y-axis, okay? And so we have a hypotenuse, that's the long side of the triangle. We have a y and an x, okay? And then we have an angle and an angle. I'm going to call this angle theta and this angle phi. We're going to talk a little bit about these things. The most important thing that you need to recognize here is, how do you find x, how do you find y, or how do you find the angle theta or the angle phi? Now, y, well, I'll start with x. X is the hypotenuse times cosine theta. And y is the hypotenuse times sine of theta. Okay? Now, that's simple enough, but that is the thing that people have an issue with. However, x is also the hypotenuse times sine of phi. If I were to measure from this point, this angle, x would kind of take the place of y, right? And y would take the place of x. Okay? All well and good. It turns out that these give us a few kind of cool things. We get that cosine of the angle is x over h. And sine of the angle is y over h. And tangent of the angle is actually sine over cosine, which, if you see here, the h's will cancel, and you get y over x, okay? This is SOHCAHTOA. What it means is sine is opposite, where y is the opposite, over hypotenuse. And cosine is adjacent over hypotenuse. This is the adjacent side, x's. And tangent is opposite over adjacent. So it's SOHCAHTOA, if you remember that. Oftentimes, you'll be given the hypotenuse and the angle, and you need to find the x length, or you need to know the y length. And here's why. I'm going to talk about this more when I talk about vectors, but here's really why. When we have a vector usually at some odd angle, and we need to know what's happening along the x direction. Why? Why do we need to know along the x? Because all motion, even as complicated as it is actually motion in the three directions, x, y, and z. And we can decompose our motion into the x motion, the y motion, and the z motion. Furthermore, if we have a force in the x direction, it only affects the motion in the x direction. There's no way for it to affect the motion in the y or the motion in the z. We'll talk about what that all means. So we need to be able to take apart vectors. And in this particular example, our vector would be our hypotenuse. Whatever our hypotenuse is our vector, and it's at an angle from the x-axis of theta. And therefore, we can break it into its x component and its y component. We'll get to that, but that's what we need to know about here. One other thing that you should note is that all the interior angles have to add up to 180 degrees, okay? That means 90 plus theta plus phi. If theta were 30 degrees, phi would be 60. If theta was 45, phi would be 45. If theta was 80, phi would be 10, okay? All the interior angles have to add up to 180 degrees. That's sometimes helpful and useful. This part here of changing between theta and phi, we're going to use pretty quickly. Next week, we're going to have to change what angle we're using. We're going to have to rotate things. And when we rotate things, we have to change the angle that we're concerned with to make things easier. So make sure you really understand this page. If you aren't that used to doing any trig, any right triangle trig, make sure you understand that. I just went through this, but sine of the angle is y over hypotenuse. Cosine of the angle is x over hypotenuse. And tan of the angle is y over x. Now, we're going to talk about this, but let's say I knew that h was 5 and y was 3. So I know that sine of theta is 3/5. So how do what do I do to get my angle? I don't know what my angle is though, okay? What do I do to get my angle? That's the inverse trig if you've never used them on your calculator. So if I have that sine of theta is, what was it, 3/5? If I take the arc sine of both sides of this equation, I get that my angle, the arc sine and the sine cancel, and I get my angle is the arc sine of 3/5. If I plug that into my calculator, arc sine of 3/5, it sometimes looks like a little minus, sometimes it's called arc sine. This is 36.87 degrees, okay? Or if you put it in rads, it would be 0.6435 rads, okay? So often we need to figure out what an angle is, knowing y and knowing the magnitude of the vector. We'll talk about that when we talk about vectors. But inverse trig cancels the trig function, but you do it to both sides. Whatever you do to the left, you do to the right. Okay? So we can get rid of the sign by taking the inverse sign of both sides. That's really, really useful. One way to see what's really going on here is cosine of what angle equals 1? You should know that this is 0, right? Okay. So you're saying, if I take the cosine, the arc cosine of both sides, what I'm saying is, what value of cosine gives me 1? That's what arc is doing. It's asking what value of theta gives us 1. And obviously it's 0. If you put it into your calculator, you should see that it gives you 0. A word of warning about all this trig stuff though, particularly tangent, but almost everything, many, many times you're going to run into what's called a multi-valued function. Tangent's an easy one. If I put tan of 3/5 into my calculator, okay, sorry, arctan of 3/5 into my calculator, I'm going to get 0.54 rads, which another way of saying 30.96 degrees, okay? So why is this not giving me the right, oh, I'm sorry, never mind. Because it wouldn't, I'm being weird, it's late. But this tangent might be 30.96, or it could be 210.96. Tangent gives you one of two angles and they're separated by 180 degrees. Whenever you use tangent, you need to double check yourself. We'll have examples later in lecture of when this happens. This also will happen with the law of sines sometimes. You have to draw a picture and you have to have it make sense. Because basically what we're saying is, if this is opposite over adjacent, then this is 3/5, right? And what if it was -3 over -5, right? Arctan of -3 over -5 gives me bad syntax. Gives me 30.96 as well, but that angle would actually be -5 and -3, okay? So this is telling me that these both have the same exact angle, but they don't. This one is actually at 210 degrees. It's 180 degrees off. So just be careful. That was the fastest example I could think of to give you. When it comes up in lecture, I'll make sure and highlight it. But just know, double check your angle whenever you use tan or arctan, and make sure you don't need to add 180 or subtract 180 degrees from it. So now, as I mentioned at the beginning of this lecture, tomorrow's quiz will be on law of cosines. Make sure you understand law of cosines. We're going to do an example in a minute, but the law of cosines is basically used whenever you have some oblique triangle, okay? And you know at least two of the sides at an angle or all three of the sides. There is a subtlety here. There's a very, very, very important subtlety here. This equation, number one, each of these angles is labeled A, B, and C. But how do you label them A, B, and C? So we typically label this little c and this, I'm sorry, I did that backwards. We typically label this length from here to here as little c, and this angle is our big C. This one is B, and so this angle is our big B, and this is A, so that's A. The point here is you have to label it that way. So if you were given A and B and angle C, and you wanted to find little c, you would have to take the angle to be the angle across from little c. Okay, just make sure part of that quiz is going to be labeling it correctly, making sure that you can put the variables in the right spot in this equation. I want you to note that what happens if this is a 90-degree angle. If angle C is 90 degrees, cosine of 90 degrees is 0, and you get c squared is a squared plus b squared, which means you get a right triangle. Cool. All right. There's also something called the law of sines, which you can invert this. You'll see it either way. That is that the law, or that the sine of an angle over the length A, or the sine of the angle B over length B. I'm not going to prove that to you. I'm sure they prove it to you in your calculus book. I'm not going to go through that proof. We may do the proof of the law of cosines on an exam. So we're going to leave that one alone as well. There's a lot of really nice ways to prove the law of cosines, and it's mostly useful if you don't know an angle, but you have some lengths. So it's useful to have it as a tool in case you need to find an angle somehow, some way, right? And you'll see that right now. So I'm going to do an example here. Let's imagine we have a triangle, and we know that this is 9 meters, and we know that this is 12 meters. Okay, if I can write M. And we know that this is 25 degrees. And what I want you to do is I want you to find this angle, and this length. Okay, so we note that c squared, a squared plus b squared minus 2ab cosine of the angle of c. So we're going to call this length c that we don't know. We're going to call this angle c, and this angle b, and this angle a. Because this length is little a, and this length is little b. Okay? So our little b equals 12, our little a equals 9. A is 9, b is 12. We want to find c. C is therefore the square root, if I take the square root of both sides, of 9 squared plus 12 squared minus 2 times 9 times 12 times cosine of 25 degrees. Okay? And when I do that, I'm going to save you the trouble of having to pay attention to all this. What I get is I get that C is 5.407 meters. Okay? One quick note, anytime we do square roots in this class, you better get a positive number under that square root. If you don't, you've done something wrong. Or I did something wrong when I assigned the problem. Square roots with negative signs are imaginary. When you take something like complex numbers, you'll find out that what that means is in a rotational plane, there's some kind of rotation. We're not going to deal with that though. We're going to ignore negative numbers or assume that we've done something horrible. So we found C. So now we know A and B and C. And what's left is finding B or A. And there's a couple ways we could do them. You could, for instance, plug in. We know that if I do B squared is equal to A squared plus C squared minus 2AC cosine of theta B. So notice here, I've changed from C to B and angle C to angle B, and I changed A and B to A and C. You can do that. If I plugged in all these numbers, I would get, I'm sorry, I could also do this for A. A squared is equal to B squared plus C squared minus 2BC cos theta A. I can solve this for cosine of theta A, and that's what I'm going to do. I would get A squared minus B squared minus C squared, just moving these two over, then divide through by minus 2BC. okay, is equal to cos theta A. If I then take the arc cosine of both sides, I get that theta A is arc cosine of A squared, minus B squared minus C squared over 2bc with a minus sign. And if I plug in those numbers, I get 64.7 degrees. Okay, so I now know that I have 24.5 degrees and I have a 64.7 degrees. And my final angle out of this has to equal what? All the interior angles of a triangle add up to 180 degrees, or pi rads, if you have them in rads. And therefore I have 25, let me actually do this way instead. Has to be angle A, angle B, and angle C. And I know that angle C was 25, and I know that this was 64.7. So if I want to solve this for angle B is 180 minus 64.7 minus 25. That's about 89.7, which this is 90.3 degrees. Okay, so angle B is almost 90 degrees, which is pretty cool. I don't know, maybe it's obvious, maybe it's not obvious. But as you can see, these problems are a lot of kind of easy math. This is a lot of what we do. You have to be able to identify A, B, and C correctly, and your angles A, B, and C correctly. Use the equation correctly, meaning that the variables have to be put in correctly. What is A, what is B, what is C? Each time it changes based on what angle you're trying to find, right? Because C and angle C change to A or B. And then using the idea of 180 degrees is the sum of all interior angles, you find a third angle. But the math itself, this math is actually pretty easy. There's not a lot of calculus going on here at all. But knowing how to do this, knowing how to set this up, there's a lot of pitfalls, a lot of ways you can go wrong. And I think this is a really good, easy first problem to get you thinking in a physics way, okay? You could also have done this with sine, the law of sines. Someone invariably will. If you're doing it with the law of sines and you're getting something weird, it's because the law of sines sometimes also has a multivariate or multi-valued angles. You might be getting 180 degrees off, just like with tangent. So you got to be really careful with sine. Law of cosines and law of sines are covered in a trig book. They're usually covered in your calculus book. They are covered in our book, very briefly. If you're having trouble with it, look it up. There's a lot of examples of law of cosines on the internet. But it's super useful as a tool to find angles that you may need, and you may have no other way to get them. And that, unfortunately, is the name of the game. A lot of problems in physics, you're looking at it and you just don't have enough information. And you go, wait, I know those angles. So once I get that angle, the problem's solved. And that's how you solve it. You find that angle. So another thing you've probably all forgotten, if you knew it, you may not have forgotten this stuff, but the double angle formulas at the bottom here, yeah, if you remembered those, good on you, because I never did. So first things first, even though it starts up here with sine, you know this is Pythagorean theorem. So this says that cos squared plus sine squared is 1, right? Which is obviously true. And this is also c squared is a squared plus b squared if you have a right triangle where this is c and this is b and this is a, or x and y and h, or whatever you want. It all comes from the same thing. If I multiply through by h squared, then I see that I get this stuff back. In fact, all those double angle formulas come from that Pythagorean theorem. Like I said, if I multiply through by h squared. I get h squared cos squared theta plus h squared sine squared theta is h squared. And remember that this is x squared, this is y squared, this is h squared, which is exactly c squared is equal to a squared plus b squared. That's pretty easy. The reason why sine of a negative angle is negative sine comes from the fact that if I go up, I have a positive angle, right? And if I go down, I have a negative angle, okay? Therefore, if sine goes below, it becomes negative. But more importantly, this is something called a right-hand coordinate system. And in a right-hand coordinate system, the x-axis and the y-axis, positive, go like that. And as we rotate counterclockwise, backwards, around from x back to x, we know that the angles increase positively. You've done this for the last, all through high school, you learned this, that this was how you set up your graph or your axes. And if you go this way, you go negative. Further, in 3 directions, you always have to draw x coming out, y going to the right, and z going up. These are obviously the positive, right? And therefore, as angles turn, and we can draw the negative x and the negative y and the negative z, as angles turn this way, they are positive angles. As you go from x to y, you're going positive, and as you're going that way, you're going negative. Okay, so negative sine means that we're turning backwards. It picks up a negative. However, negative cosine of this is still going to be the same because cosine is positive over here. On the right-hand side of the y-axis, cosine is positive. On the left-hand side, it's negative. But above the x-axis, sine is positive, and below, it's negative. Therefore, these hold true. Okay? It becomes important because sometimes our argument isn't tan, it's actually a function. And if our function is negative in sine, we can pull the negative out. If it's negative in cosine, we can ignore it. And that's really helpful. This is super helpful as well. Let's say I have a function that is x plus cos of x is equal to 5. Can I solve this? Maybe. I may or may not be able to solve that. Better yet, what if I have sine of x plus cos of x is equal to 5? Can I solve that? And the answer is no, I cannot. I can multiply through by sine perhaps, or get a tangent out of it or something. We're going to see this crop up when we're doing projectile motion really soon. We're going to do projectile motion, and we're going to see that occasionally we end up having a sine and a cosine in our answer, and we have to convert them into sine of double the angle. We'll also use it to prove maximum range and maximum height stuff. But again, it's a tool for you to have. It's a tool for you to remember and just write down somewhere. And then if you ever get into trouble, see, this is called a transcendental equation. Sometimes you can't solve transcendental equations. You have to solve them numerically, iterating through solutions. Those of you who are taking differential equation classes probably know that they're basically different functions, so you can't convert them unless you have some double angle formula or something like that that will help you. And we'll talk about that when we get there. But just know that the one we mainly use is this one, that 2 times sine of theta, cos of theta, or sometimes we'll end up with sine of theta, cos of theta is equal to, say, 4. And so we know that if we multiply both sides by 2, this becomes sine of 2 theta is 8. And therefore we can take the arc sine. And so 2 theta of arc sine of 8 gives us the answer. I don't know if I can take arcsine of 8. Knowing my luck, that's out of domain. Yeah. If it's 8 radians, so arcsine of 8, nope, still out of the domain. Let's make this 0.3. So this becomes 0.6. So arcsine of 0.6 is 0.64. So therefore 2 theta is 0.64 divided by 2, and I get that theta is 0.32 radians. So it's useful because you can solve equations you otherwise wouldn't be able to solve having that cosine hanging on there. We'll talk about those. Thankfully, those pop up during specific types of problems, and you always know they're going to happen and you know how to solve them. It's one of the rare, really nice times that you just know what to do and you do it and move on. Okay. I want to speak a little bit here about another tip or trick. If you don't know, if you haven't had a lot of experience with angles and you don't have a calculator, one thing, you can actually remember the more common angles. So if this is 0 degrees and this is 90 degrees, okay? Another way to say this is pi half and this is 0 radians. And then if we go 30 and 60 and, I'm sorry, 30 and 45, so this is 45 degrees, this is 30 degrees, this is 60 degrees. We know that this is pi third, this is pi fourth, and this is pi sixth. We know that because it's a third of 180 degrees, and there's pi radians at 180 degrees. Okay, so let's make a quick chart here. 0, 30, 45, 60, 90. This is also 0. This is pi 6. This is pi 4. This is pi third. This is pi half. And we want cosine and sine, the values of those. Well, it turns out that when cosine of 0 is 1, and sine of 0 is 0, and cosine of 90 degrees is 0, and sine of 90 degrees is 1. You know those. Additionally, this is root 2 over 2 at 45 degrees. They're equal at 45 degrees, cosine and sine. So that only leaves us with 30 degrees and 60 degrees. And we only have 2 values to choose from. We either have 3/2 or 1/2. Now root 3 is clearly greater than 1. And if you look at 30 degrees, you can see that the x, the cosine part, is definitely longer than the y part. So therefore, the y gets the 1/2, and at 60, it's opposite. And so now, without having a calculator, if you need cosine of 60 degrees, you know it's a half. If you need cosine of 45 degrees, you know it's root 2 over 2. Or it's 1 over root 2. If I multiply top and bottom by root 2, I get 2 over 2 times root 2, and the 2 cancel. So if you know those values, you can use them in a problem and save yourself some time of putting things into a calculator. If you're one of those people that can memorize stuff really well, memorize it. The other thing, as we already noted, in quadrant 1, cosine and sine are both positive. In quadrant 2, cosine is negative, sine is positive. I know that looks like a little Y or cactus or something. In quadrant 3, they are both negative, and in quadrant 4, cosine is positive and sine is negative. Otherwise, these values stay the same when you rotate through. They basically go backwards. So this is at 90, then this is back to 120, 135, 150, 180, right? And then it goes back the other way, going this way with the flip of signs. So there's really not much to remember. If you can draw it on a test, you don't have a calculator, you don't want to waste your time with the calculator, or you just recognize, oh, that's sine of 30, that's a half. And you don't have to put it into your calculator. It will save you time on things like the MCAT. It's a useful trick when you're going into standardized tests. They'll often give you values of sine or cosine that are 60 degrees or 30 degrees or 180 or 150 or whatever, intending for you not to need a calculator and recognizing those values. So you probably don't want to memorize it if you don't know it already. If you knew it and you forgot it, remember it. Maybe write it down on a little cheat sheet somewhere and keep it next to you when you're doing these problems. It'll save you time, save you calculator time, and that's always useful. So now we're getting to stuff that isn't remedial. So as I said at the beginning of this, the language of physics is vectors. Scalars are numbers, but they're more than that. They're quantities of things without direction. They're mass. Mass is how much stuff is in an object. Mass doesn't have a direction, okay? Water in a pool doesn't have a direction. The displacement of water flowing out of a pipe definitely does. The blood in your veins flows out or into your heart. As you walk home, you constantly change direction. All sorts of things. A ball going up, okay, that's thrown upward has a velocity vector upward. It also has a position vector upward, and it has an acceleration due to gravity down, okay? The velocity vector changes, and eventually it slows down and becomes 0, and then it heads back the other way. The whole time the acceleration vector is constant and down. It's the acceleration of gravity. We need to know what direction the velocity is in. More than that, if we were to launch like a cannonball, or we throw something to our friend, we throw a ball on an arc path, a projectile parabolic path to our friend, we notice that what is actually happening here is V is actually a combination of V in the X and V in the Y. In the Y direction, the ball just goes up and comes back down. In the X direction, the ball heads that way. And if you basically combine those two motions, if it's traveling to the right while it's going up and down, you get a parabolic path. We can always divide our vectors up into their component vectors. Usually those will be X, Y, Z directions for acceleration or velocity or position. And then we can associate those things to each other and get meaningful information. And we'll see that in a minute. But the main idea here is that vectors don't just have magnitude and direction, they have components. They have components in X direction and Y direction and Z direction. And those components can be treated individually. So what's a little weird here is that you're gonna see vectors are written two different ways. You can write a vector, okay, as just a magnitude. Or you can write where in this magnitude, it has Vx in the X hat direction plus Vy in the Y hat. And this is the last time I'm gonna write it this way because I find it redundant and dumb. When I write Vx, I mean the velocity in the X direction. When I write Vy, I mean the velocity in the Y direction. That's what these subscripts mean. Another thing that, to peel back the curtain a little bit, I used to always write my vector signs. But I actually read a really good book on teaching physics, and the instructor was talking about how vectors can actually confuse students. They inherently understand what a vector quantity is, that it has a magnitude, it has a direction, but that's what we're talking about. And so the signs are just an added complication that doesn't need to be there. And there's some really good reasons to leave them off, I believe. So I tend to not use them unless I want to be explicitly clear that I'm talking about a vector. So please forgive me. I hope it doesn't hurt you down the road if you get like your next instructor yells at you about not writing vectors. My apologies, but I tend not to write. What is important is that Vx plus Vy plus Vc, I shouldn't have written this, by the way. So a velocity is made up of its components, but it's also has a magnitude that is the square of each of its components. And so what this tells us is that we can break a vector up. And in fact, almost all the vectors, I would say 99.9% of the vectors in this class are only going to have one or two components. Then we can break them up just like a triangle. So let's say that this is our x-axis, right? The ground, and I launch something with a speed of 15 meters per second at 30 degrees. Okay, I want to know what its x velocity is, and I want to know what its y velocity is. So all I have to do is I write v. I know the magnitude of v. V times x is the cosine of 30, and y is the sine of 30. Now, sine of 30 is that the half or the root 3 over 2? It's the half. So this is 7.5 meters per second. Okay. You can double check that if you want, just to make sure I didn't mess up. But I'm pretty sure I'm right. And then 15 cosine of 30 is 13, about 13 meters per second. Okay, so we have the x velocity and the y velocity, and then we can treat them separately. We can do different things with them. We can add them, we can multiply them. Multiplication is very weird with vectors. We're going to talk about that in a minute. But when we cover chapter 3 tomorrow, we're going to do a whole bunch of vector addition stuff. So I'm just going to lightly talk about it. I'm not going to go into really much of an example. Just know that if I had a vector A, let's say, at some angle, and then I had a vector B at some other angle, okay? So this, first of all, I can draw a parallel x-axis here, and I will get angle 2. So this is angle 1, and this is angle 2, and this is my B vector. So I would have that A was AX plus AY. It has components in the X and the Y direction, right? And vector B is BX plus BY. But these are A cos theta 1 plus A sine theta 2, and this is in the X hat direction, and this is in the Y hat direction. And this is B cos theta 2. I'm sorry, this is not theta 2, this is also theta 1. There. Come on. In the X hat plus B sine theta 2 in the Y hat. And here's the thing. When we add these, we get A plus B is AX plus BX in the X hat direction, plus AY plus BY in the Y hat direction. If we were to subtract them, this would be minus and this would be minus, but you would still add them. You'd still write them as added together. The magnitude of A plus B would be the square root of AX plus BX squared plus AY plus BY squared, right? And a component of, I'm going to write it like this, A plus B in the X direction would be that. And the component in the Y direction would be that. So we would get that the angle, right? The angle of A plus B would be AY plus BY over AX plus BX. So it works just like a normal vector. You just add the components together or subtract the components from each other and leave them as components. That's pretty easy to understand. Probably the simplest idea here would be you walk 1 meter in the X positive direction and then 1 meter in the Y positive direction. What is A plus B if this is A and this is B? Well, your new vector has an X component of 1 and a Y component of 1, and it's basically root 2. So this is A plus B, and A plus B would be 1 squared plus 1 squared, square root of that, which would be 2, square root of 2. When I talk about vectors, when we do chapter 3, I'm going to go over how to properly add and subtract vectors. Much, much greater detail than this. All I want you to take away from this is you are adding the components and you are getting a new vector. So this leads to a vector, a new vector that is A plus B or A minus B. Turns out that there's a lot of little things that you have to pay attention to, make sure that you do right, that you don't like mess up the directions. And in fact, we have a lab that's all about vectors and drawing vectors that we're going to do. It's a long, kind of grueling lab, but it's actually really beneficial for those of you that don't quite understand vectors. And we're going to do that. That'll probably be our third lab. Our first lab will be graphing. But anyway, so let's move on. We got that part down. We're going to come back to multiplying them in a minute. I want you to make sure that you remember how to do the quadratic formula. So if we have a quadratic equation, any equation, it could be AY squared plus BY plus C is 0. It could be anything weird. It could be, you know, AT squared plus BT plus C, right? Is 0. The point is you have something with a power squared, a single power, and a constant. From that, you can use the quadratic equation to find the roots of this equation, which means the values for which t, if t is that value, the equation becomes 0, or x is that value, it becomes 0. The only notation here that you need, well, the only thing that you need to worry about is b squared minus 4ac cannot be negative. If it ends up being negative, something is seriously wrong in your equation. You've got a negative sign somewhere, you've forgotten a negative sign, something weird is going on. That means that 4ac can't be bigger than b squared. Just as a check, if that happens, something is seriously wrong. Okay, so let's do an example here. We're given x squared plus 3x minus 18. We want to know what the roots of this are. And we see from this that a is 1 and b is 3 and c is minus 18. C is this whole constant term, b is the constant in front, a is the constant in front. In this case, it's 1. So we plug in for b, 3. B squared is 9 minus 4 times 1 times negative 18. So this negative 4 times 1 times negative 18 all becomes a positive term. Over 2 times a, which is 1. We see that we get two numbers because there's a plus or minus here. The root ends up being 9. So we get negative 3 plus 9 over 2 or negative 3 minus 9 over 2. Negative 3 plus 9 is 6 over 2, which is 3. Negative 3 minus 9 is minus 12 over 2, which is minus 6. And from that, we get that our answer is 3 or minus 6. If this were time instead of x, let's say this was t squared minus 3t minus 18. And these often come up when we're doing projectile motion. Does a time of negative 6 seconds, I guess, make sense? And the answer is probably not. So you have to recognize that one of your roots usually doesn't make physical sense. It doesn't occur during the time that we care about. Why this would happen in projectile motion is there's going to be a time I should draw this a different way. Usually this will happen when you have something that's like launching off a cliff and hitting the ground. And so we want to know when this value becomes 0, what is t? And so you'll have a time where it previously was t, and you'll have a time later when, when it previously was at 0, and a time later when it was at 0. And that will give you a positive and a negative root there, or a positive and a negative, root to the quadratic. Choose the one that makes sense, if you can tell. For those of you who know how to factor and don't need to use the quadratic formula, note that our answer does give the correct term. If I put in 3 into this equation, I would get 0 here, and therefore the whole thing would be 0. If I put -6 in, I would get 0 here. And this being the case, I get x squared, I get -3x plus 6x, which is 3x, and then I get -3 times 6, which is -18. This is really just a refresher. Make sure that you know it. Now, this is something that some of you who probably have a lot of math might not actually have ever done before. And if you haven't done it before, this might be a cool trick that you really, really like. So the idea of simultaneous equations is when we have 2 equations with, or more equations with at least 2 variables. So imagine I have x minus 5y is equal to 9, and I have 3x plus y is equal to -5, okay? There's a couple ways to go about this. In physics, you'll always hear us talking about we need as many equations as we have unknowns. And that's so we can substitute things in. Otherwise, you can't solve them. You could have more equations than unknowns. You could have 5 equations and only 1 unknown. And then you could choose whichever one you wanted to solve it. But you at least need the same number of equations as unknowns. In this case, that's what we have. So we can solve the top equation for x, and we get that x is 9 plus 5y. We can put that in for our 3. So we get 3 times 9 plus 5y, plus y is equal to -5. This is 27 plus 15y plus y is -5. If I move the -27 over and I put these together, I get -32, and I get y is -2. If I substitute back in y is -2 here, I get -2 times -5 is 10. So I get that x is 9 minus 10, which is -1. And I know that y is -2. Does that solve both of my equations? -1 minus 5 times -2 is 10. -1 minus 10, or plus 10 is 9. 3 times -1 is -3. -2 is -5. Yes, it solves it. Great. However, there's actually easier ways that require you're a little bit more sophisticated. So, we can actually multiply both sides of this equation by 3, and we get 3x minus 15y is equal to 27. We can then subtract this whole equation. The equal sign comes down. So remember, everything picks up a negative sign. This becomes a -27, so this is a -32. 3x minus 3x is 0. The -15 becomes a +15, so this becomes 16y. We get y is -2. Solve it the same way, plug y as -2 in, and you're done. You can find that x is -1. The other way to do it would be you could add. You could multiply this top one by 15 and add them. But it's something that I think people forget they can do. It's often much quicker than substituting in for x or y, just to add the 2 equations together and eliminate one of them. It's called Gaussian elimination in like linear algebra. You learn it. You probably learn it other places, but just know that you can do it. The last thing that I want to show you is, so I'm going to use these two. 3x plus y is equal to -5 is -5 minus y, and 3x with a negative sign is 27 plus 15y. Now notice, I should really do this. No, stop. Now notice, okay, if I do this, I'm basically dividing them. Instead of adding and subtracting, I'm dividing. And this side becomes -1, and this side becomes -5 minus y over 27 plus 15y. Another way to see that is I multiply through by -1, and I set them both equal to 3x, which means they're equal to each other. Move that, and what I get is 27 plus 15y is -5 minus y. If I move this y over and I move to 27, I get 16y is -32 again. Y is -2. There's a lot of little tricks that you can use in arithmetic that you probably never used that make things super easy to solve. Play around, find things, find cool ways. Sometimes it's a really clever, fast way to solve a physics problem. Okay, just keep that in mind. And there are definitely situations where it is the fastest way to get to a number is by dividing or adding or subtracting equations. And you can do it. If you don't want to do it, I'm cool with you just substituting. Back substituting is fine. Solve one of them for y and plug it into the other one. Solve one of them for x and plug it into the other one. It's a nice trick. It saves some time, so I wanted to bring it up. All right, back to vectors and multiplying. So, the funny thing about vectors, and that is that they do not, unfortunately, they don't multiply like normal things do. In fact, we're going to, when we talk about multiplying vectors, we're talking about multiplying with something called a dot product. And the point here is that they don't multiply like just two numbers. They do, but they don't. So let's imagine I have a vector A and a vector B, and there's some angle between A and B, okay? If I want to know what happens if I multiply A by B, I get this AB cos theta, where theta is the angle between A and B. It doesn't necessarily have to be the angle to the x-axis. I could have some x-axis here, and I could have A, and I could have B, okay? This is that angle. There could be some other phi angle from X to B, or phi from the ground to A, whatever. The angle I'm talking about is the angle between the two vectors, right? In fact, to prove this, if I place A along the x-axis, and I'll prove the second half of it later, okay? And B is here, component-wise, I multiply these guys. This is the other way of writing. And now we know that AX is simply A, and BX and BY is B cos theta and B sine theta. Now, there is no AY. AY is 0. Therefore, A dot B is AX, A times BX times B cosine of the angle between them, and this term becomes 0. This sum, though, is not a vector. It's a scalar. We're going to most often, or first, really see this in work, where you have a force acting over a distance. And basically, if you can imagine, we're pushing something in that direction, and we apply a force at some angle, okay? Only the amount of force in the direction of the motion, because we assume that the object can't move up or down, only the amount of force in the direction of the motion, that's the only thing that's putting energy into the system. The amount of force acting perpendicular doesn't do anything. This is also sometimes called the projection of B onto A. So it's kind of like the shadow of B. Bx is kind of the shadow of B on A. Zoom out that A and B overlap. So if B and A were 90 degrees apart, right? If B was straight up and A was along the X and B was along the Y, they would be 90 degrees apart. The dot product between them would be 0. They don't affect each other. Therefore, if two vectors are perpendicular, meaning that they are 90 degrees off, the dot product is always 0. That's also useful to know. It actually helps solve some other problems. But for now, just know that when we talk about multiplication of vectors, we're talking about a dot product. We multiply the components, we add them up, and the answer is a scalar. In terms of force, what we get is we get newtons times, or force times distance, work. We get newtons times meters, which is energy. And energy doesn't have a direction. But whenever you multiply, whenever you dot two vectors, you get a scalar. So sometimes the dot product is called scalar multiplication, just to help you understand. So let's do a quick example of a dot product. A and B are vectors that have magnitudes of 4 meters. So let's draw them. I'm going to switch to red. So A is along the x-axis, and it's 4 meters. That means its magnitude is 4 meters. And B is along a line 30 degrees off the x-axis. Okay. So A is 4 meters, and it's in the x-hat direction only. Otherwise, another way of saying this is AX is that, AY is 0. BX is 4. Remember, they both have the same magnitude. 4 times cosine of 30. And BY is 4 times sine of 30. Now, I know their magnitudes. A and B are 4. So I can do A dot B is A magnitude, B. Sometimes when you take like a vector analysis class, this is how they'll write it. So this is 4 times cosine of 30. And you end up with something like 13.856 if you multiply this through. 0.856. I guess it would be meters squared, it's like area or something. But it's a scalar. It has no direction, okay? So we could also do it the other way, which is A dot B is equal to AX times BX plus AY times BY, right? I guess I don't want to write it like that, but AX and BX is 4 times cosine of 30, 4 times 4 cos 30, plus 0, and again, same answer, 13.856. I want to show you something a little bit important here. So now, imagine it instead, okay? I'm going to rotate this thing through. So this is still 30 degrees between them, A and B, except I've rotated the whole thing up 60 degrees. So B now lies along the y-axis. And therefore, BX is 0 and BY is 4. AX and AY, AX is now 4 cos of 60 and 4 sine of 60. And I still want A dot B. So A dot B gives me AB cos of the angle between them. And the angle between them is still 30. They're still magnitude 4. So this is still 4 times cos 30. That answer is still the same. AX and BY, or BX plus AY BY, I know that BX is 0. So I get AY is 4 sine of 60 times 4. But sine of 60 is equivalent to cos of 30. If you look at the right triangle that we drew, if this is 60, cos, this is whatever cos of 60, and this is 30, then this is sine of 30. And if this is sine of 60, then this is also cos of 30. This is sine of 30. Okay, so sine of 60 is equivalent to cos of 30, which means we get the same answer as before. The only thing that matters is the two vectors. Doesn't matter which way you multiply them in the dot product. You simply multiply either their magnitudes together or multiply by the angle between them, the cosine of the angle between them, or you multiply their components. And remember, always a scalar. Big takeaway, always a scalar. What you end up with is some kind of just number. All right. Next up, we're almost done. We're getting there. Multiplying vectors, cross product. And so now what we have to talk about, and we're going to use those same two vectors, is something called a cross product. And in a cross product, what you do is you're actually causing rotation. Cross products are rotations. In a weird way, A dot B, okay, is AB cos. A cross B is AB sine. So in a weird way, A dot B is multiplying the parallel parts, the parts that are in the same direction. And A cross B is multiplying the components that are perpendicular to each other. If you take linear algebra, you can get this I hat, J hat, K hat, AX, BX, AY, BY, AZ, BZ. Take the determinant of that matrix and you will get this. But this is A cross B. You can see that when you cross product, you end up with a vector, and the vector can have multiple components. However, we're going to assume that we're only in the x and y plane, and that means we have AX and we have BX and BY. Those are the only components we have. We have no Z. Those terms are gone. Those terms are gone. So these are the only terms we have left. And more importantly, we don't even have AY. So really what we get when we do our A dot B is we get AX, BY in the Z hat direction. We'll talk about what that means in a minute. But AX and BY, remember that we said these were 30 degrees apart and they were each 4. So this is 4 cos 30, 4 sine 30, and the magnitude of AX was 4. So this is 4 times 4 sine 30. And it's positive. If we had switched these, if we were doing either, if this was A and this was B, and we were doing A cross B, right? A would have an AX and an AY, but B would only have a BX. And you can see that this term right here would actually be negative, okay? There's one thing that you can do, because the sign's always going to be an issue. The second thing you can do is something called the right-hand rule, which we're going to get into. But basically what's happening here is we have a vector A and a vector B, and we're rotating A to B in a counterclockwise direction in this case. Because we're rotating A to B, we're crossing A to B, so A cross B gives us a positive rotation. I'm just going to put a theta for that rotation. It's positive just like with the X and Y axis, right? If you're going this way around, it's positive. If you were going the other way, it would be negative, like we talked about earlier. Now, B cross A, if we were to rotate B to A, this would be a negative rotation. One way to do that, one way to see that, okay, is I know you probably can't see my hand, but I'm going to try to show you here. So I'm holding my hand up, pointing out at you. The right-hand rule says that if your thumb points in the positive Z direction, the direction that your fingers curl is positive, okay? So, and we'll go back to that. So what we need to look at is here, okay, the positive Z direction comes out of the page, out. So point your thumb at your chest and how your right hand only, not left hand, if you turn your fingers, if you curl your fingers around into your palm, that's the direction A is turning to B, and that is positive. Now, if you turn the other way, which is kind of hard to do, I generally hold my arm out, point your thumb towards the screen, you'll notice that your fingers curl the opposite direction. They curl clockwise. That is negative. They curl in the direction here, they would be going that way. That way is negative, that way is positive. That is called the right-hand rule. What this means, in effect, is imagine that you had a rod that was attached to like a cylinder, like a wire or something, so that it could rotate either way around. If I push it with a force here, right, this distance is my R, and I take the cross product of R cross F, what I get is I get R and F, and I put them tail to tail, and I rotate R to F. I always rotate R to F. We'll cover this a lot more when we go to torque after exam 1. But you rotate R to F, and this thing swings around in a counterclockwise motion, which we are defining to be positive rotation. All of that is going to be gone over laboriously again when we get to torque. I just wanted to introduce it here. For now, what I want you to know is that the cross product is given by this identity, and if you need it, you can break it into these components, and the last thing to remember is the cross product is a rotation, and it's a vector perpendicular to both of the other vectors. So if we're in the X and Y plane only, the cross product gives you a vector that is in the Z plane, perpendicular to X and perpendicular to Y. In 3 dimensions, Z is up, X is out, Y is to the right. And therefore, X turning to Y gives you a positive rotation, Y turning to X gives you a negative rotation. It's weird stuff, really, really weird stuff. And we're only going to really see it when we do torque. But it's interesting. It's a kind of weird thing. It's kind of a weird pseudo vector. For those of you that are really studying math, you need to understand that the cross product, the vector that it gives you, is a weird vector. There's some issues with it because it doesn't reflect correctly, that you can study up on and do some cool, real cool stuff with. And the history behind the cross product is fascinating. But for us, for the rest of you that aren't really all that into math, when we get to torque, we'll go over this again. For now, plug and chug it. Make sure that you know how to find the magnitude of any vector is ax squared plus bx squared plus, sorry, I'm being weird. I know, thank you. A y squared plus a z squared, and so it's each of the components squared added together. That's the magnitude of A or B, and the cross product is A, B, sine of the angle between A and B. This also tells you that if you do all that component stuff and you divide it by the magnitude of A and B, you can find the angle between them. If for some reason you knew all that component stuff, I don't remember exactly what the math review problem involving the cross product is, But if you're interested, it's fun. It may be new math to you, although I'm pretty sure you cover it in like Calc 2 or Calc 3. And we will definitely use it when we get to torque. And it's also fun because you get to look weird to all your friends while you're trying to figure out whether something's rotating positive or negative. If you ever wonder why physics students are always like doing weird stuff with their hands, we're usually trying to figure out which way something's rotating. Anyway, onward. That's right-hand rule stuff. Few more. We're almost done. These are going to go quickly because you guys already have the calculus. Basically, we're going to use calculus to derive equations that we will then use to solve problems. We will rarely be doing actual derivatives. You will rarely be doing actual derivatives. However, you'll be using them and understanding them. And basically, we're going to start this whole class off with derivatives, as Isaac Newton talked about. So you need to understand that if I start at x1 and I travel to x2, I say my displacement is x2 minus x1. And if I divide that by the time, I get what is called my average velocity. Okay? And so if I were to plot a whole bunch of these points, right, I could get these little averages, right? Well, that's kind of helpful. I mean, I guess I could take x1 to x13 and divide it by the whole time, right? But really, we want to know what's happening in a moment. And in a derivative, what you do is you take closer and closer x values. You know this, I know you know this, but you take them closer and closer to where what you get is that v is delta x over delta t. But if you allow delta x and delta t to go to 0, in that limit, in the limit as that happens, you get dx dt. Is the velocity, is the speed, instantaneous. So one thing that you have to say is you have to specify the time in this case when we're taking a derivative, but you guys know that. It's a limit. When you take successively smaller time intervals and x intervals, you get the instantaneous velocity. When you take the velocity, dv dt, and I should really write it like this, the time derivative of the velocity is the acceleration. And we'll talk more about this when we talk about Newton's laws on Wednesday. But really, that's what we're doing. We're taking derivatives, which are rates of change. In this case, the change of position with time, the derivative of the position with time is velocity. Okay, so if I have a function that says x of t is 5t squared, dx dt at t is equal to 1, I take the derivative with respect to t of x. Well, that's obviously 10t. And I take it at a time of 1, that's 10, right? That means that at a time of 1 second, my instantaneous velocity or speed, although we're going to talk about why we don't want to really use that, is 10 meters per second, right? Which is cool. Really, really cool. Okay. Yeah. The derivative is a limit because that's mathematically how you define a derivative, by taking successively smaller and smaller increments of time to where it goes to 0 and you get instantaneous. If you didn't do that, you'd have averages. All right, we're all good on it. We're going to come back to that in a minute, but I want to talk about graphs before we do that. You understand, I think, that a linear equation is y is mx plus b. This is the equation of a line. We're going to need that right now. Okay. Oh, wait, sorry. I jumped ahead of myself. Make sure you know your common derivatives. And by common derivatives, I mean, like power function. I take the derivative of this is my function, right? And so I take the derivative of f of x with respect to x, I will get 3x squared. That's a power function. Trig functions, the derivative of cosine with respect to theta is negative sine theta. The derivative of sine with respect to theta, sine theta, is cos theta. Ln of x is 1 over x. E to the x, the derivative with respect to x of e to the x is just e to the x. The derivative of a constant is 0. A constant doesn't change with time. So d dt of a constant, sorry, I can't spell, of a constant has to be 0. Derivatives are rates of change, and constants aren't changing. Make sure you review your chain rule stuff in case you need it. X sine of x. If I want to take the derivative with respect to x of this function, what do I get? First, I hold x stationary, and I take the derivative of sine, which is cos. And then I hold sine constant, and I take the derivative of x, and I get 1. So plus sine x. I don't know why I wrote theta there. Shoots to it. Okay. So remember how to do chain rules. Fairly common stuff. We're not going to get too crazy, and when we do, I will take you through it if we're doing something really crazy. But just understand that the derivative is the rate of change with respect to some variable. We'll occasionally need to use theta or time or x or whatever. We'll make that clear. We're going to do a fairly quick one in a minute, but for now, just keep it in mind. You guys know what derivatives are. You've all had calculus. I need to talk about graphs, because how derivatives are related to graphs. So we can't lose sight of the fact that we are doing physics, we're doing science, we are taking observations about how things work and making predictions. And how you store that data is in a graph. I want to make it really clear that when we say y versus x, or we say x versus t, we mean exactly that. We mean y versus x, or we mean x versus t. Now, we might have some data that we collected, monitored, whatever. And this is y as a function of x, okay? And this line, if we put a line through here, we say we're gonna put a linear line. And that linear line is mx plus b. I'm gonna ignore this for now, but b is the intercept, meaning it's where this crosses. So let's say b is 0. So what we get is y is mx. Or we get y over x is m, where m is our slope. And we can see here that our slope is our y over x. And if we take this to be our slope at an instantaneous point, what we actually get is we get the derivative of y with respect to x. Okay? The instantaneous slope at any particular moment gives us the change of y with respect to x. So on an x of t graph, our slope, m, would be dx dt, which is our velocity. So if we note your position with time, how far you're traveling as time goes, at any particular point, we can find out by looking at the slope what your instantaneous velocity at that point was. And that's how we use graphs to understand what is going on. We graph x versus t, and then we take the slope and we get our v. Our slope appears as x is equal to mt plus b. We assume that we can ignore b, and we write down the slope as x over t is v. That's what we do with graphs. Graphs always are labeled as y versus x, or x versus t. Whatever is in your left-hand horizontal column, or vertical column, comes first in the title of your graph. The slope of a linear graph gives you the linear relationship. If you had a quadratic, right, you could have like a t squared plus bt plus c. Again, this is your initial when, in this case, when x was 0, where the particle was. And your b of t, right, this is your velocity, your instantaneous velocity, and this is actually your instantaneous acceleration. We'll talk about that later when we do some graphs, but just know that that's what we're going to do a lot in lab, is we're going to take graphs and we're going to use them to extract position or velocity or acceleration out of those graphs. So let's go back to this. We know that dx dt is our velocity, and similarly, v versus t graph, the slope, the linear slope will give us the acceleration. We assume that that's going to be constant in this problem. Assuming a is constant, like for instance, we're doing free fall or projectile motion, and a is g, 9.81. Knowing that, we get these equations. All I did was I multiplied by dt on both sides. If I were to integrate this, okay, and I integrated from time naught is 0 to time final is t, so this one goes 0 to t, and this goes v initial to v final. I can see that this is v final minus v initial, right? And this is a times t. That's it, okay? But I really want to say that this is my v, and this is v initial plus a t. I want to move that t back to a little t. It looks better. It's the way it's written in the book, blah, 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 blah. Now, if I do the same thing here, x initial, x final, t initial to t final, where little t will be my t final, and t initial will be 0, and I plug in that, I get x final minus x initial, and I have to integrate v initial plus at times dt from 0 to t. If that bugs you, they're different t's. This ends up being v initial t plus a t squared over 2. Now, when we integrate, we do an antiderivative. The derivative kind of kicks down the power. The antiderivative brings it up. So an integral basically like adds 1 to a power. It goes back up in scale 1. It does a lot of other things, though, that you may not have ever thought about, okay? It's the area under the curve, and you know that. I know you know that. But what does that mean, okay? So let's say that I have a v and t graph, right? We already said the slope of a v and t graph would be the acceleration. But what's the area under the curve? Well, it's v times t. It's the area under the curve. And if v was, say, constant and t was, like this was 5 and this was 10, well, v times t is what? It's meters per second times seconds, or meters. So the area under the curve, which is the integral, gives us x. It gives us x. That's important to know, okay? Just remember that when you're integrating, the area under the curve gives you the product of y and x on your graph. The slope gives you the derivative of y with respect to whatever x is, okay? You can also see that for the area under a curve, cosine starts here, goes underneath, and comes back up, right? And this is at 2 pi, and this is at 0. So if we did cosine of the angle, right? If we integrated from 0 to 2 pi, cos theta d theta, this integral, kicking that up, it has to be negative sine theta. I'm sorry, it has to be sine theta. Sine theta becomes cos theta. And we go from 0 to 2 pi. Sine of 2 pi is 0. minus sine of 0, 0. This whole thing is 0, but the area under the curve is also 0 because this part is negative. So we get 0. Same thing with sine. A sine wave looks like this, equal amounts. So just understand that. Understand what you're doing when you do an integral. We're going to have a lot of easy integrals to do if we do them at all. You're going to see them in derivations, like I said. The only times I can really see using them is if we're finding center of mass or we're finding something else like that. So I've already basically done this. Antiderivatives of some common functions. We did that. Make sure you know like sine and cosine. So the integral of sine, the integral of cosine. Integrals of powers, right? So x dx is equal to x squared over 2. You add 1 to the power, divide by the new power, add a constant unless you have limits of integration. All well and fun, or not fun. But basically, you're going to see them when we're deriving things in lecture. You're probably not going to have very many integrals to even deal with, if at all. We're more interested in the rate of change and how things are changing, how the velocity or the acceleration or the position are changing. And so that's what we care about. So again, knowing that A is dv dt, is the acceleration is the time rate of change of the position, and that this is a constant. So A is a constant. If I take dv is a dt, and I take this from v naught to v and 0 to t, what I get is I get v minus v naught is a t, right? It would technically be 0 to t, but t0 goes away, so I don't care about that. This is actually our first constant acceleration equation. If we then use that v is dx dt, the time rate of change of the position, we get, again, dx is v dt, taking the integral of both sides from x initial to x final, from time 0 to t final, and putting this v in here, where v is v naught plus at. What I get is I get x final, minus x initial is v naught t plus at squared over 2. That is our second constant acceleration equation, which gives us the change of position is equal to the initial velocity times time plus the acceleration times time squared over 2. We're going to go over that in detail later, but they're there for you if you want to look at them. There's a lot more integrals you can do, but I'm assuming that you've seen all sorts of really hard ones. We're not going to have very hard ones. We're going to have some pretty easy ones to do when we get up to them, and we probably won't get to them. So anyway, this lecture I know was super, super long, and I'm sorry for that. But I wanted to make sure that you had everything necessary. Make sure you go through and check out all the math stuff. If you want this to the end, then you're obviously interested. There's a lot of help on the Wiley Plus website. Tomorrow's quiz is on law of cosines. Just know how to do it. If I give you a problem with 3 lengths or 2 lengths in an angle or 2 angles or whatever, know how to, I guess not 2 angles, but something like 3 lengths or 2 lengths in an angle. Know how to find the other angles. That's it. And the point with those quizzes is just so that you can assess whether or not you know how to do log cosines. And if you don't know how to do it, you can get on it and learn. As always, if you need help, contact me. My info is in the syllabus. And good luck. Hope you learned something today. Stay safe, stay healthy. I'll talk to you tomorrow.